this video, we are going to talk about Fischer projections and also how to assign R and S on Fischer projections. Let us consider this molecule in perspective. Now, how do we draw this molecule in Fischer projections? What we must notice is that in Fischer projections, it is a way of representing a 3D molecule in a 2D. So, what we will do is that with this molecule, with Fischer projections, all the groups that come on the vertical line are groups that are pointing away from the viewer, and all the groups that come on the horizontal line are pointing towards the viewer. So in this case, you can see that this proton is pointing away from the viewer, and therefore if we draw it in Fischer projections, it is going to appear on the vertical line. So another way to redraw this molecule here is by drawing it like this: CH2, CH3, and then this one too is also pointing away, and then the OH is pointing towards the viewer, and then this CH3 too is pointing towards the viewer. So this is how we redraw it in terms of Fischer projections, and therefore all these groups that are pointing away from the viewer is going to be on the vertical line, and all these groups that are pointing towards the viewer is going to be on the horizontal line. And therefore, in terms of Fischer projections, this is going to look like this. Let me draw it here. So the OH, it is pointing towards the viewer, so it comes on the horizontal line, and this CH3 too comes on the horizontal line, and then this proton will come down here, and then this CH2, CH3 will come on top. Now, after you've drawn a molecule in perspective in Fischer projections, the most important thing is to check the configuration of the molecule. If the molecule was S in perspective, you have to ensure that it is also S in Fischer projections. And if it was R in perspective, it must be also R in Fischer projections. Now, if the molecule is not the same configuration in perspective after drawing it in Fischer projections, then there are some allowable rotations that you can do to push the molecule in the correct configuration. So one of them is by rotating the molecule by 180 degrees. And then the second thing is you can hold one group. And then you rotate the other three groups. Let's assign configuration to this molecule. So you see that oxygen is number 1, then the ethyl group is number 2, and the methyl is number 3, and then the proton is number 4. Proton is already pointing away from us, and we are moving from 1 to 2 to 3 in the clockwise direction, and therefore this molecule is R. Let's determine the configuration after we've drawn it in Fischer projections. Here is 1, then the ethyl group is 2, then the CH3 is 3, and then the proton is number 4. So what is the configuration here? One most important thing is that in Fischer projections, the least group must always be on top. In this case, we can see that the least group, which is this proton, is not on top of the vertical line, it is rather down. So what we must do here is that we must rotate. If we rotate this by 180 degrees, we are going to put this proton here. So let's rotate this by 180 degrees. So the proton comes on top here, and then the CH2, CH3 comes down here. and then this OH comes here, and then the CH3 also comes here. So you see that by this rotation, we've placed the least group on top of the vertical line. Now let's determine the configuration. This is 1, this is 2, and then this is 3. So from 1 to 2 to 3 in the clockwise direction, it makes it an R. So the perspective molecule is an R, and then the Fischer projection is also R. So this is a correct Fischer projection drawing of this molecule. Let us consider this molecule. What is the configuration of this molecule? Is it an R or it is an S? So if you assign groups, this is 1, and this is 2, and this is 3, and then the proton is 4. However, we said that in assigning configuration, the proton must, or which is the least group, must always be on top. But in this case, it is on the horizontal line. So what we must do is to do an allowed rotation that puts the proton on the top. But in the allowed rotation, what we can do is that we can hold one group. You see that in the previous example, we rotated it by 180 degrees, and that didn't change the configuration of the molecule. In this case, we are going to hold one of the groups and rotate the others to put the proton on top. So let me draw the rotation here. So we are holding the OH, then rotating the other 3. If we rotate, the proton comes here, and then this COOH comes to the bottom, and then the CH3 comes to the side. Let's determine configuration in this case. This is 1, this is 2, this is 3, and then the proton is pointing away from us, and therefore you can see that this is also an R. What is the configuration of this molecule? So you can see that in this molecule, let's assign the groups. Chlorine is number 1, and then this is number 2, and this is number 3, and this is number 4. Number 4 is not on top of the vertical line, so we must do allowed rotation to put it on the vertical line. And what we can do is that we can hold the chlorine and then rotate the other 3. So let me draw it down here. So I'm holding this chlorine. If we rotate the other 3 in the anti-clockwise direction, the CH3 comes here, and then this one goes there, which is CHO, and then the proton comes to the top. So after we are done with this, we can now determine configuration. The chlorine is number 1, then the CHO is number 2, and then the CH3 is number 3. So you can see that it is moving in the clockwise direction, and therefore the configuration of this is an R. What is the configuration of this molecule? So you can see that the least group, okay, so let's assign the groups. This is 1, and then this side is 2, and then this is 3, and then the proton is 4. So in this case, the least group is not on top, and because it is not on top, what we can do is we can do an allowed rotation in this situation. Or the other thing is that we can also determine the configuration and reverse it, because the proton is pointing towards us. And remember that in previous examples, we've established that if a proton is pointing towards you in determining an R or S configuration, then what you do is that you determine the configuration, and after that you negate it. So in this case, it is 1, 2, 3, which is going in the anti-clockwise direction. So this is an S. But because this proton is not at this place, then we need to reverse the configuration so that this becomes an R. Let's come to this situation. Here's number 1, and then here's number 2, and then and this is number 2 because this carbon has a bromine which has a higher molar mass than a proton in this case. So here's number 2, and this is number 3, and then this is number 4. So in this case, it is 1, 2, 3. It is going the clockwise direction. But the proton is not pointing away from us. It is rather pointing towards us. And therefore, instead of an R, we will negate the configuration, and then it will become an S. So here is an R, and this place is an S. Let's try naming this compound. So we can see that the longest chain will be this. The carbons are 1, 2, 3, 4, 5, and therefore it is a pentane. And then in assigning the various numbers, here is 1, then here is 2, and this carbon is carbon 3, and then this is 4, and then this is 5. On carbon number 1 we have one. On carbon number 2 we have a bromo group, and then on carbon number 3 we also have a chlorine group. In terms of alphabet, B comes before C. So the bromine is at 2R. So this becomes a 2R and then 3S. We put that in brackets. Then we'll get 2 bromo and then 3 chloro pentane. So this is the name of this molecule. Let's consider the above molecule. Let's draw this molecule in Fischer projection. So as usual, the chlorine group is pointing away from us, and then the CH3 is pointing towards us. So we need to, let me draw it here. So the groups pointing away from us are the chlorine group, Cl, and then this ethyl group, CH2, CH3. And then the group pointing towards us are the CH3. And then this proton is also pointing towards us. So this is how we draw it. Then we can then convert it into Fischer projections. So by just drawing a 2D vertical and horizontal line, and then this part becomes a CH2, CH3, and then here is a proton for this, and this is CH3, and then the down here is a Cl, chlorine group. But let's determine the configuration of this molecule. This is 1, this is 2, and this is 3. And then the proton is number 4. But you can see that in this case, the least group is in the perspective of the molecule. And therefore, what we've said is that if it is in the perspective of the molecule, we need to swap this proton, the positions of the proton and the chlorine, and then we swap the other 2. I will put the link to the previous video where I explained how to determine R and S configuration in the description below. So that means that this part, this chlorine becomes number 4, and then this proton becomes number 1, and then we change these 2. So here becomes number 3, and then this becomes number 2. So let me put asterisk on the changes we've made. So we change here from 1 to 4, we change here from 4 to 1. So there's an asterisk here. And then we change here from 3, we change here from 2 to 3, and we change here from 3 to 2. So if you can see, it is moving from 1, 2, and 3. So this is moving in the anti-clockwise direction, and therefore this molecule is an S molecule. And because it is an S molecule, we need to also ensure that the drawing on the Fischer projection is also S. So let's assign groups here. However, Okay, so this is 1, and then this is 2, this is 3, and then this is 4. You can see that on the Fischer projection, it is not an S because 1, 2, 3, it is an R here. This configuration is an R. But then, because the proton is pointing towards us, because it is on the wedge bonds here, then we need to reverse the configuration. And so that instead of an R, this is an S. So the perspective drawing is an S, and then the Fischer projection too is also an S. Let's go ahead and name the molecule. So this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So this is a butane. And then we have a chlorine, that is 2S on carbon number 2. So it becomes 2S. We put it in a bracket. 2-chloro. And because there are 4 carbons, it is a butane. So 2S, 2-chlorobutane. So let's consider this molecule. Let's determine its configuration and possibly try naming the molecule. So you see that in this case, this is CHCl2. And therefore, here is number 1. And then this is CH2, then C. Here is number 2, and this is number 3. And then the proton is number 4. 1, 2, 3 is going clockwise direction. However, because the proton is pointing towards us and not pointing away from us, we need to reverse the configuration, and therefore this is an S configuration. Let's try naming this. How many carbons are there in total? So here is number 1 carbon. So let me put it here. 1 carbon, 2 carbon, 3rd carbon, 4th carbon, and then there are 2 carbons here. So the 5th and then the 6th carbon. So 6 carbons, and that makes it a hexane. However, we have a substituent here, which is a methyl group, which is a substituent, and there is a 2S configuration here, so we need to show it. So we are going to put 2S, and then, but there is 2 chlorine groups here, and then there's also an iodine substituent over here. In terms of alphabet, chlorine comes, C comes before I, and therefore the chlorines are 2, so it's going to be 1,1 dichloro. And then the iodine is on carbon number 4, so 4 iodo. And then the methyl is on carbon number 2, 2 methyl. The total number is 6, so it is hexane. And therefore the name of this molecule is 2S 1,1 dichloro 4 iodo 2 methyl hexane. Let's consider this molecule. We are going to determine its configuration and then convert it into Fischer projection and then name it. In this case, chlorine is number 1, the ethyl group is number 2, and then this is number 3, and then the proton is number 4. So this is 1, 2, 3. It is going anti-clockwise. That is an S. But because the proton is pointing directly towards us, then we need to reverse the configuration. And if we reverse the configuration, this is an R. Sorry. First it was moving 1, 2, 3 in the anti-clockwise direction as an S. So if we reverse the configuration, it's going to go in the clockwise direction, and this is an R. So this molecule is an R. Let's convert it to a perspective. Let's convert it to a Fischer projection. And what we do is that this proton is pointing away. So this proton is pointing away from us. And therefore I'm putting the proton somewhere here. And then this chlorine too is also pointing away. So the chlorine is here. But this ethyl group is pointing towards us. So I'm going to put the ethyl group. Sorry, the ethyl group is pointing away from us. So I'm going to put it at the top here. And it's the same for this CH3. So that one too is also pointing away from us. And therefore, in terms of Fischer projection, this is going to look like this. This is CH3. And then this is a C2H5. A Cl. And then a proton is here. And let's see if the configuration here too is an S. This is 1. And then this is 2. And this is 3. So the configuration is 1, 2, 3, which is an S. But because the proton is not pointing away from us, we need to change configuration. And if we change it, it's going to point in the clockwise direction to make it an R. So the perspective molecule is an R configuration. And then the Fischer projection is also R. Now let's try and name this molecule. So the carbons, this is carbon number 1. This is number 2. And the third carbon and then the fourth carbon is on this ethyl group. But we have a chlorine on carbon number 2, and the configuration on carbon number 2 is an R. So what we need to do is that here is a 2R, then 2 chloro. We have 4 carbons in total, so it's a butane. And therefore, this is 2R, 2 chlorobutane. Let's talk about how to convert molecules in perspective to Fischer projection. So let's consider these 2 molecules. How do you convert this into Fischer projection? What you do is that, let's take this first molecule. You need to first rotate the molecule 180 degrees. So if you rotate one side of the molecule by 180 degrees, it will align with the other side, and we can then draw it into Fischer projection. So in this case, you see that this proton is going into the page. So this one is going into the page, and then this CH3 is coming out of the page. But if you rotate it by 180 degrees, the CH3 now goes into the page, and then the H comes out of the page. And therefore, this molecule will look like this after the rotation. We see that this CH3 is coming out of the page, and therefore I'll represent it with a wedge bond. So this is CH3. And then this proton is going into the page, so I'll represent it with a dash bond. We didn't do any rotation to this side of the molecule. The rotation only happens at the top. And this proton is here. This CH3 is coming out of the page. After the rotation, it will go into the page. The CH3 is now on a dash bond. And this proton is going to the page. After rotation, it will come out of the page. And therefore, we need to put that on a wedge bond. So there is a proton here. And then after we are done, we will put our eyes here. If we put our eyes at the side of the molecule, you see that our right eye will be viewing the bonds that are coming out of the page, and then our left eye will be viewing the bonds that are going into the page. And therefore, let's draw the Fischer projection. So this here is a proton, and this is a proton, because this is in the plane of the molecule. So our right eye will be seeing this. So we are starting from here, and therefore this carbon is this carbon. So our right eye will see this proton, so it is on the right. And then our right eye will also see this CH3, so this CH3 is also on the right. And our left eye will see this CH3. So this CH3 is here. And then our left eye will see this proton, and this proton is here. So this is how to draw this molecule in Fischer projection. The first thing is to rotate one side of the molecule by 180 degrees. And when you do that, all the wedge bonds become dash bonds, and all the dash bonds become wedge bonds. Then you put your eyes here, and then starting from this carbon, you draw the rest of the molecule. Let's apply the same thing here. You see that this is in the plane of the molecule, but this proton is coming out of the page, and this one is going into the page. And then this ethyl group is going into the page, and the CH3 is coming out of the page. So it means that after rotation, the CH3 will go into the page, and then the ethyl group will come out of the page. So let's go ahead and draw it. And this is a CH2, CH3. It's in the plane of the molecule, and this is a proton. And then there's one proton which is going into the page. So this proton is going into the page. Then this proton is coming out of the page. So let's show it here. And then here, after the rotation, because we are doing 180 degrees rotation, this CH3, which was coming out of the page, will now go into the page. Therefore, here's a CH3. And then this ethyl group will come out of the page. So this is an ethyl group, CH2, CH3. And what we'll do is that we'll put our eyes here. If we put our eyes there, we can then go ahead and draw the Fischer projection. Let me draw the Fischer projection here. Now if we put our eyes here, you see that in the plane of the molecule, the down, because this carbon stands for this carbon, it represents this carbon. So here's a proton, and then at the top here is this ethyl group, which is CH2, CH3. And then if we stand here looking at this carbon, then our right eye will be seeing this ethyl group, and therefore the ethyl group is going to be on the right. And here is a CH2, CH3. And then this proton 2 will be on our right, because it will be seen by our right eye. But this CH3 will be on the left, viewed by the left eye, and this proton 2 will be on the left. Predict the configuration of the stereogenic centers and convert the following perspective structures to Fischer projections. So let's determine the configuration. Here's 1. This is CH2OH, so that is 2. And this is 3. And then the proton is number 4. You can see that this is going in the clockwise direction, and therefore the configuration of this molecule is an R. Let's draw this molecule in Fischer projection. So what we'll do is that we'll put our eyes here and view it from this side to this side. Now if we put our eyes here, let's draw the Fischer projection. This CH3 will come to the bottom, because we are looking at it from this side to this side. And then this C2OH, CH2OH will be at the top here. And then you see that our right eye will be seeing the OH, so the OH will be on the right. And then our left eye will be seeing this proton, it will be on the left. So let's determine the configuration here and see whether we are correct. Here's 1, then this is 2, and this is 3, and this is 4. So it is going this way, S. But remember that the proton is facing us. It is not at this point where it is going out of the page, and therefore we need to reverse configuration. So the configuration of this molecule to is R, and therefore this is the correct drawing of the Fischer projection of the molecule. So let's come to this part, the B part. What we need to do is to flip this molecule upside down. If we flip the molecule upside down, remember any rotation we do, all the wedge bonds become dash bonds and the dash bonds become wedge bonds. So let's redraw this molecule. And therefore, this is a CHO. And then the methyl group will come here, CH3. Then this bromine was on a wedge bond, but after we are done, it will come on a dash bond. So the bromine is here. And then the proton was on a dash bond. After rotation, it will come on a wedge bond. So we'll put our eyes here and look from this side to this side. So let's draw the Fischer projection here. So you see that the CH3 will be at the bottom here, and then the CHO will also be here. Then our right eye will be looking at the bromine, and our left eye will be looking at the proton. And let's determine the configuration here. Bromine is 1, and then CHO is 2, CH3 is 3, and then the proton is 4. So it is going the anti-clockwise direction, and that is an S. However, proton is facing us, so we need to reverse the configuration. So this is an R configuration. Let's determine the configuration here. This is 1, this is 2, and this is 3. So it is going the anti-clockwise direction, which is an S. But the proton is on a wedge bond, and therefore we need to reverse configuration so that this will be an R. So this configuration too is an R. So the Fischer projection is correct. Let's come to this molecule. So you see that this molecule is straightforward. So we need to put our eyes here. If we put our eyes there, this part of the molecule, which is CH2OH, will come down, because always we are looking at it from this side to this side. And the CH3 will go on top. So here's a CH3. And then our right eye will be viewing the proton. Then our right eye will be viewing this proton. So this proton is on the right. And then our left eye will be viewing this bromine. So the bromine is on the left. And then when we come here, our right eye will also be viewing an OH. And the left eye will be viewing this proton. So this is the Fischer projection. So let's try and determine the configuration here. Here is 1, this side is 2, and then here is 3, and then this is 4. But so in this way it is R, but the least group, which is the proton, is on the dash bond, and therefore we need to, the least group, which is the proton, is on the wedge bond, so we need to reverse configuration. So this part is an S. Let's determine configuration here. This is 1, and then this is 2. This is 2, so the 2 is already here. Let me write the 2 here. So we have a 2 here, and then this is 3, and then the proton is 4. So it is going in the anti-clockwise direction, and the proton is already on the dash bond. So this is also an S configuration. And let's come to the Fischer projections we've drawn. So let's take this carbon for example. So this is 1, this is 2, this is 2, this is 3, and then this is 4. So 1, 2, 3. It is going the clockwise direction, R, but the proton is pointing towards us, so we need to reverse configuration, and that is an S. So, and this carbon stands for this carbon. Let's come to this one too. This is 1, and then this side is 2, and here is 3. So it is also going in the clockwise direction. But we need to reverse configuration because the proton is pointing towards us, and therefore this one too is an S. So you see that here is SS, and the Fischer projection is also SS. So we are right. Let's come to the last aspect. And this part too is also straightforward. There is no rotation we need to do. We only do rotation if these groups which are pointing up here were pointing down, so that we'll get it well. So in drawing the Fischer projection, we are always look in this side, so our eyes are here. So this CH2 OH is in the plane of the molecule, and this part is a CH3. So if we put our eyes here, our right eye will see the OH, and then our right eye will also see this proton. Then our left eye will see this proton, and the left eye will also see this OH. Let's determine the configuration here. So here is 1, and then this is 2, and this is 3. The proton is already on the dash bond 4. So this is an R. It's moving this way. And let's determine configuration here. This is 1, and then this is 2. There's an OH here, so there's this little OH here. This is 1, this is 2, and this is 3. So it is moving anti-clockwise, S. But the proton is pointing towards us, and therefore we need to reverse configuration to make it an R. So this one too is an R. So here's RR. Now let's determine configuration here. This is 1, and this is 2, this is 3. Sorry, this is 3, and then this is 4. So it is moving in the anti-clockwise direction, S, but the proton is pointing towards us, so this is an R. And let's determine configuration here. This is 1, this is 2, this is 3, and then this is 4. So it is moving from in the anti-clockwise direction, which is an S, but the proton is pointing towards us, and therefore we need to change configuration. Here's an R. So you see that here is RR, and this place too is RR. So the Fischer projections are also correct. Draw both the perspective and Fischer projection of the following compounds: A, S1 bromo 2-methyl butane, and then B, R1 cyano 1-phenyl ethane. So let's look at bromobutane 2-methyl. So let's draw a butane here. This is a butane. Then he's saying that a 2-methyl butane. So this is a 2-methyl butane. So there's a CHBr at this part, and then there's an ethyl group here, which is a CH2, CH3, and then there's a methyl group. So let's put the methyl group on the wedge bond. There's a CH3 here, and there's also a proton that I didn't show. There's a proton here. So let's put the proton on the dash bond. But let's determine the configuration over here and see. You can see that this is 1, this is 2, and this is 3. You can see that this is an S. 1, 2, 3, and then the proton is 4. It is already going there out into the page. So this is moving in the anti-clockwise direction. This is an S, and therefore this is a correct drawing of the 1-bromo 2-methyl butane. Let's come to phenyl ethane. So we have an ethane group. So let me represent it with. So this is an ethane group. We have R1 cyano. So there's a cyno group here, and then one phenyl. There's also a phenyl group here, and then there is a proton, and here's a CH3. Let's draw the perspective of this molecule. So the cyno group is here, and then the metal is here. Let me put proton on the dash bond, and let me put the phenyl on the wedge bond. So this is a phenyl. And let's check the configuration of this molecule. So this is 1. So this is 1, this is 2, this is 3, and then this is 4. 1, 2, 3. That is an R. So you can see that this is also a correct drawing of the R1 cyno, 1 phenyl ethane. And let's convert this to perspective. So in terms of perspective, we'll put our eyes here. We put our eyes here. Starting from here, this is a CHDR. And then our right eye will be seeing the CH3. So the CH3 will be on the right. And our left eye will be seeing the proton. And then this is a CH2, CH3. But let's check the configuration here and see whether it is correct. Here is 1, this is 2, and this is 3. So it is moving, that is an R, but the proton is pointing towards us, and therefore we'll negate this, and this is an S configuration. Now let's come to this molecule. So let's draw the Fischer projection. We'll put our eyes here, and starting from here, a Fischer projection will look like this. So the cyanide group will be at the bottom, and then this side is a CH3. Then our right eye will be seeing the phenyl group, and our left eye will be seeing the proton. So let's determine the configuration over here. This is 1, and then the phenyl group is 2, and then the CH3 is 3, and then the proton is 4. So this is an S, but because the proton is not pointing away from us, but rather pointing towards us, the reverse configuration to make it an R. So this is an R, and this is an S. So the question says we should draw S, 1 bromo, 2 methyl butane, and that's what we've drawn. The perspective and the Fischer, and the same for R1 cyno, 1 phenyl ethane. So this is the perspective, and this is also the Fischer projection.